3 of these planets. In Venus, the greenhouse warming is ridiculous, so it's hot enough on the surface to melt lead, so it's a completely hellish place. Mars, there isn't nearly as much carbon dioxide, but there is some greenhouse warming. But the interesting thing, you'll notice in the Earth spectrum, you have these bits of thing in the spectrum, ozone and water. And if you saw those in a distant planet, this bit of the spectrum tells you you've got oceans, and this bit of the spectrum tells you you've got life, because the oxygen is made by living things. When the Earth was first formed, this ozone band wasn't there in the spectrum. It only appeared after living things came on the planet. So that was fun. That's a way, if you make a telescope that can look at this infrared part of the spectrum and look at planets of other stars, you could see if they have life on them. So that entertained me for a while, trying to think of spacecraft to do that. And NASA picked up this, and this mission called Terrestrial Planet Finder was the kind of infrared interferometer that you need to look for life on other planets. Okay, so a few years ago, I began to think we should look at what we can do that's serious in space. And that means something about climate change, because this is a plot you should all be familiar with. This is not a NASA data plot, it's Earth data over the last 1,000 years. So the temperature was sort of very slowly cooling, which is what we expect, because the Milankovitch warming of the Earth is actually going down at the moment. But then in the last few decades, the temperature has shot up. And for those of you who haven't got religion yet about this, there's a correlation between temperature and carbon dioxide. And here it is from Antarctic data over the last few 100,000 years. These are the interglacial periods and the glacial periods. So the Earth is mostly cold and a little bit of time it's warm. And what's interesting about the data from Antarctica is that carbon dioxide and temperature are absolutely in lockstep. And right now, the carbon dioxide is going off scale here. It's going straight up with no sign of stopping. And if you don't know anything about anything, and you just say, well, maybe temperature and carbon dioxide go together, then you predict, this is 20 degrees Fahrenheit here, so you predict we might be going up 10 degrees Fahrenheit, whatever, right? I mean, it's just from the correlation that we know already exists. And another very interesting correlation is between temperature and the level of the ocean. So during the glacial to interglacial period, the temperature varying by 6 degrees centigrade here, and sea level varying by 120 meters. And so if you just imagine that that correlation between temperature and sea level continues, then it only takes 4 degrees Kelvin centigrade to melt the rest of the ice, which is like 60 meters. So without having to have any big computer models or anything, just look at what the Earth has done in the past and look at where we're headed with carbon dioxide and temperature in the future. It's, we're looking at potentially some pretty awful things happening. And so the worst things that can happen are the irreversible things. If you melt the sea ice, if you melt the poles, then it takes 100,000 years for snow to fall in Antarctica to put it back again. So you do not want to go there, right? Because otherwise you're stuck with a 60-meter increase in sea level, and probably a major loss of species like the events that we've seen in the past. So in my view, things are very serious. And if there are things to be done in space to mitigate what seems to be coming up on the horizon, then those are the things that we ought to be doing in space. Well, already the space agencies, NASA and ESA and whatever, do a terrific job of monitoring climate change. And that's a very important role. Perhaps the most important role that NASA does at the moment is to see what's happening. but it's a passive role, right? You just sit there and you watch the ice melting and the temperature going up and so on. But is it like the weather? You know, lots of people complain, but nobody does anything about it. Well, there is the possibility. There are two directions in space where you can do something about it. And that's what I want to spend the rest of the time looking at. So, this is why I've stopped thinking about all the fun stuff with NASA. I think it's frivolous now. So we're not looking for jobs to keep people going or making money or whatever. We're looking at saving this planet. So I would say, forget the moon. Look at modeling. I mean, NASA in New York, the Goddard Institute for Space Studies, Hansen there is one of the great guys in predicting and calculating climate change. That's a great job for NASA, but monitoring the effects. But the two possible things you can think about to do something about climate change. Can you generate solar power in space and relay it to the Earth? Is that going to be a way to stop using fossil fuel? Or if things get desperate, if we're headed towards catastrophic, irreversible effects on the planet, then one way to stop that in its tracks is to shade the planet. And you can do that from junk in the atmosphere, or you can do it from space. And so one of the things I did recently was think about, is it feasible to cool the planet in space? So I'll just go through very quickly. I think I'm going too slowly here. Space solar power, the idea is you can put solar panels in geosync orbit, make the power into microwaves, beam it to the Earth. And the important thing compared to ground solar power is that you get sun all the way around the orbit, so you can shine the power to nighttime or to any area of the planet, whether it has sunshine or not. So these gadgets have been devised. This is 6 kilometers, this is 1 kilometer. This thing makes 5 gigawatts of power delivered to the Earth. You can beam it down to centers where you distribute the electricity from those centers. But the numbers look pretty awful. You have to get launch costs down to, in a NASA study, from the present $20,000 a kilogram down to $400 a kilogram, and get everything else cheap, then you just about get on scale to make money and to be competitive. The bogey, you've got to get to 10 cents a kilowatt hour, which is the present price of fuel. So this study, which was for six of those 6 kilometer satellites, you actually need about 100 times that amount of electricity to make a difference on the planet. So unless there is a huge change in launch costs, this ain't going to work. That may happen, but the thing about energy is that there's no premium on where the energy came from. You can't sell boutique energy for more money. Right? Nobody wants to pay more for a kilowatt hour because they know it came from space. They just want to buy energy. So unlike the Hubble telescope, which gets sort of different stuff from ground telescopes, space solar doesn't produce anything different in the product. So one of the things I thought about, and I gave a talk about this at MIT a few years ago, was that as an alternative to having all this junk in space, the 6 kilometer circle and the microwave and whatever, maybe you can generate the power down here, turn it into microwaves down here, but you don't have to launch any of that stuff, and then just beam the microwaves up to mirrors in geosync orbit, and then direct the light down again. So the picture is slightly different from what we had before. This time in the day side of the Earth, you make solar power and microwaves, beam them up to the mirror, same size mirror, 1 kilometer, and then just reflect that down to wherever it's wanted. So that reduces by about a factor of 20 the mass and the cost of what you have to put into space. So I was getting pretty excited about this, and I was going to write a paper and get famous about it, but I thought I'd better do one sanity check. That is, what you're using space for in this case is really to transmit radiation from A to B, and also to time delay it, if you like, because you can send it from the day to the night side of the Earth. So we should just check if it's cheaper to use transmission lines to do this. And currently, there's a transmission line, for instance, 1,000 miles from Northern Oregon to LA. Pretty efficient, been working for a long time, making money. And it turns out if you increase the voltage a bit to 1 million from 500,000 volts for this one, you can get 90% efficient transmission compared to 50% for the microwave. You lose a lot of energy turning electricity into microwaves and back again. And you don't need much conductor to do it. So I stopped working on this. I'm disappointed. I'm a space junkie. I would have liked to find something useful in power to do with space, but the numbers don't support it. So what you can do on the ground, and you don't even need a lot of storage, it turns out. So this very nice study in this month's Scientific American. During 24 hours, in the day you can generate the energy from sunlight. In the night you get it from wind. You use hydro in between. So it's a pretty good renewable energy solution. And what I've been doing, so at the moment, photovoltaic is not very big. This is 15 megawatts in Nevada. And what I'm working on, putting all my energy now, not in space, but in trying to make cheap solar power to fix that problem. So I'll just spend the last bit of time here talking about space sunshades. So if we get desperate, can we put something in space that will shade the planet? It turns out you need to block about 2% of the sunlight to get back to pre-industrial temperature. Well, 2% of the area of the Earth is 1 million square miles, so you need 1 million square miles of sun up there to block the sun. So this was a view from a little while. So I guess this is me here, right? But so the L1 orbit, you can put something in L1, and the spacecraft here will go around once a year exactly in line with the Earth. So if you stick something here, like junk or anything, it will shadow the Earth. You have to worry a little bit about the wobbling of the moon, but it's not too difficult. Anyway, I went through a lot of this. I didn't invent it, but I just thought, well, let's calculate really what will it cost to do this, how quickly could you do it. So one of the problems is if you just put junk at L1, it gradually drifts off. It's not a stable orbit. So you have to put spacecraft there, and they have to have just enough smarts to be able to hold themselves in orbit. So one of the things to do, that's when the moon causes the Earth to wobble. That's a detail. So I figured out how to make the lightest possible stuff that would actually serve as a blocker of the sun. And it turns out you have to be a little bit careful here. If you make really thin mirrors, people think about mirrors in space to block the sun. But if you make them really lightweight, which you can with a mirror, then the pressure of sunlight will just blow them away. It'll blow them off orbit. So there's no stable orbit at L1 for really lightweight stuff. Unless you make it transparent so it doesn't get radiation pressure. So I made a screen that's transparent, and what it does is diffuse the sunlight a little bit instead of reflecting it, and that's enough. We actually made some of this screen. This is only a few hundred nanometers thick of silicon nitride, but it's got bumps on it that make it diffuse. So you can see when you look through the screen, it's gone blurry. And in a little more detail, if you shine sunlight through the screen, just get a beam of sunlight, which is here, and then put it through the screen, the directly transmitted light gets knocked down by well over 90%, and the light gets spread out into little spectra around. And those from L1 then would miss the Earth. So you don't have to have a mirror. You can't use a mirror, but you can use this screen. Well, even if you've made it only a few hundred nanometers thick, it's still going to weigh like 5 million tons for the million square miles that you want. So you can't launch with present rockets at Saturn V cost. It's $400 trillion to launch this thing. So that, even in the present era of trillions, that's a lot of money. So you do have to find a cheaper way of launching. So I went through the calculation of how to do that. Nobody ever does magnetic launch because it's extremely violent. If you want to get up to escape velocity and you do it in a mile or so, you have about 4,000 G of acceleration. So you don't want to put people in magnetic launch. But if you want to launch large amounts of freight, then it seems like a very good way to go. It's environmentally good. You don't use you don't make a lot of energy or carbon dioxide. It's something that hasn't been developed because there's been no need for freight launch, but it could be developed. That'll get you clear of the Earth, and then you can use ion engines to get you the rest of the way. And those have now been proven out. So what does a sunshade look like? It doesn't look like some Battlestar Galactica. It looks like a lot of little things. I originally started thinking about big things in space, but if you use a lot of little things, you don't have to assemble anything in space. You can assemble it all on the Earth, send up all the little things, and then send them out into a cloud. So the little things that I came up with for this is a thing that's 2 feet in diameter. It's a complete spacecraft that knows where it is and can push itself around. These little ears have got solar cells, and they got little MEMS mirrors that can move the thing into place. So these weigh about 1 gram each, which is a little heavier than a butterfly and a little lighter than a hummingbird. And you would need 10 or 20 trillion of these. So it would be nice to try and make some of these. They work by transmitting the light is spread into a little donut instead of going straight through. So my conclusion on these sunshades were that the lifetime in space would be about 50 years. It would cost something like $4 trillion if we used the electromagnetic launch. So it's something like $100 billion a year, which is about 0.2% of world GDP a year. So in fact, the money is not really an issue if you are at the point of believing you need to do something serious to prevent disaster on the planet. It would need a lot of technical development and innovation, and one should get started a little bit with that now. At present, NASA's investment in investigating this approach has been $50,000, and I think it's probably worth spending a little bit more on it to see if it could actually, whether these calculations are reasonable. In this case, again, just like the solar power, there's a ground-based alternative, and that is putting your junk into the atmosphere. And this experiment is already done by nature. So periodically when a volcano goes off, it puts a lot of aerosol in the atmosphere, and we know from those volcanoes that actually cools the planet. So in this plot that we already saw, this little dip in the cooling of the planet, this was in the 70s when there were very dirty chimneys, and so there were sulfur particles in the atmosphere. And they, for a little while, cooled the planet. Then we learned how to clean up sulfur smokestacks, and the temperature took off after that. So this is the low-cost quickie solution that's the alternative to space. But in this case, there is a difference in the quality. In electricity, it's just how much you make. But in the case of cooling the planet by reducing sunshine, there are far more side effects that could come if you put your blocking particles in the atmosphere rather than in space. So I think the jury is out on this, and it would be good. This is the one place where if you ask, can you do something in space about climate change, I think this still has the potential to be an interesting thing to do. So that's the conclusion for these active things that you can do, I think solar is a non-starter as far as I'm concerned. It has to come from the ground. But in the shading of the planet, then maybe we should try and spend a little bit more money to see what can be done. All right, thank you.
We're going to pause for about a minute or two just to get set up. So.